In 1999, a research ship off the coast of Oregon drifted off course. It was a mistake. The crew was supposed to be collecting sediment samples along the Cascadia Subduction Zone, and instead they ended up 55 miles south, drifting straight into the San Andreas Fault Zone off Northern California. Most research teams would have written that off as a wasted detour and moved on. This team didn't. They decided to take a core sample anyway, just to see what was down there. And what came up out of that sediment, sitting in a tube on the deck of that ship, would sit quietly in a lab for over 2 decades, before scientists finally understood exactly what it was telling them. It wasn't just unusual. It may be the first physical evidence that 2 of the most dangerous fault systems on the entire west coast of North America are capable of triggering each other back to back within minutes or hours, not decades apart, not centuries apart. Minutes. If you live anywhere from Northern California up through Washington State, or if you've got family there, stick with me on this one, because this changes something fundamental about how scientists are now thinking about the worst-case scenario for the entire West Coast. Drop a comment and tell me how close you are to the coastline, because the distance actually matters a lot more than most people realize once you understand what this study found. And if you want to keep tracking every new piece of Cascadia research as it comes out, because there has been an unusual amount of it this year, subscribe now. Let's talk about what that sediment core actually showed, because the detail here is what makes this discovery so unsettling to the scientists who found it. When a major earthquake happens along an underwater fault, it triggers underwater landslides that kick up sediment. And that sediment eventually settles back down to the ocean floor in a very specific, predictable pattern. Geologists call these layers turbidites, and under normal conditions, they follow a consistent structure. Coarse, heavier material sinks and settles first at the bottom, and finer, lighter material layers on top of it as it drifts down more slowly afterward. That pattern is so reliable that scientists use it like a fingerprint, reading through decades or centuries of these layers stacked in sediment cores to reconstruct a timeline of major earthquakes going back thousands of years. But the core, pulled from that accidental detour in 1999, didn't follow that pattern. It was reversed. Coarse, sandy material sat above finer, silty sediment, upside down from what an ordinary single earthquake event should produce. It's worth understanding how these sediment cores actually let scientists reconstruct a timeline stretching back thousands of years, because the method itself is one of the more remarkable tools in modern earthquake science. Cascadia has no written historical earthquake record the way California or Japan does, since the Pacific Northwest coastline had no widespread written record keeping until relatively recently in geologic terms. So instead of relying on written accounts, geologists like Goldfinger built their understanding of Cascadia's earthquake history almost entirely from these turbidite layers, methodically, drilling and extracting core after core along hundreds of miles of the subduction zone, then cross-referencing the layers between different core sites to confirm which layers represent genuinely widespread, margin-spanning earthquakes versus smaller, localized underwater landslides unrelated to a major quake. That work is how scientists know Cascadia has produced a full margin rupture roughly every 200 to 500 years on average, with the last confirmed full rupture occurring in the year 1700. An event so well documented through this same sediment record, combined with Japanese written accounts of an unexplained tsunami that arrived without any local shaking, that scientists can date it to a specific night in January of that year. That same painstaking layer-by-layer methodology is exactly what allowed this research team to recognize that the reversed core sample from 1999 didn't fit the normal single earthquake pattern at all. Chris Goldfinger, the marine geologist at Oregon State University who has spent decades studying exactly this kind of sediment record and who led the new research built around this discovery, explained what that reversal actually means. A single earthquake wouldn't produce that layering. It takes 2. The lower, finer layer likely formed first, generated by a major earthquake along the Cascadia Subduction Zone itself. But then, before that sediment had time to fully settle the way it normally would, a second event occurred, close enough in time that it kicked up a second pulse of coarser material and laid it directly on top before the first layer had finished its normal settling process. In other words, this wasn't the signature of one earthquake. It was the signature of 2 earthquakes from 2 different fault systems, happening close enough together in time that their sediment records collided into a single reversed layer instead of 2 separate, cleanly stacked ones. It's worth pausing on the geography here too, because understanding exactly where Cascadia and the San Andreas meet explains why a synchronized rupture is physically plausible in the first place, rather than just a statistical coincidence pulled from one unusual sediment sample. The Cascadia Subduction Zone doesn't extend infinitely southward. It terminates at roughly Cape Mendocino in Northern California, and the San Andreas Fault essentially picks up right where Cascadia ends, running southward from that same general area down through the length of California. That handoff point is not a clean, simple boundary. It's the Mendocino Triple Junction, a genuinely chaotic piece of geology where three separate tectonic plates, the Pacific, the North American, and the Gorda, are all interacting simultaneously, which is precisely the kind of structurally stressed overlapping environment where stress transferred by a major earthquake on one fault has a physically plausible pathway to reach and destabilize the other. Here's why this discovery matters so much more than a single unusual sediment sample buried in a research paper. For decades, the public conversation around West Coast earthquake risk has treated Cascadia and the San Andreas as two separate stories. Cascadia is the one most people have heard called the Big One, the subduction zone, running roughly 700 miles from Northern California up through Oregon, Washington, and into British Columbia, capable of producing a megathrust earthquake in the magnitude 8 to 9 plus range, along with a tsunami that could reach the coast in as little as 15 minutes. The San Andreas Fault is the other headline name, the roughly 800-mile transform fault running through California, responsible for historic quakes like the 1906 San Francisco earthquake and the 1857 Fort Tejon earthquake, and widely discussed as the fault most likely to eventually produce Southern California's own version of the Big One. Two enormous, terrifying fault systems, but for most of the public conversation around them, two separate disasters, with two separate timelines that happen to share a coastline. Goldfinger's new research says that separation might be an illusion. As he put it, we're used to hearing the Big One, meaning Cascadia, described as this single catastrophic event on its own. What the sediment evidence increasingly suggests is that activity on one of these fault systems can actually trigger activity on the other, essentially syncing the two up into a single, compounding disaster sequence rather than two unrelated events, separated by decades. The two fault systems meet, or at least come into close proximity, near a location called the Mendocino Triple Junction, off the coast of Northern California, the exact spot where the Pacific Plate, the North American Plate, and the Gorda Plate all come together in one of the most structurally complicated pieces of geology on the entire planet. And it's precisely that complicated meeting point that appears to give a major Cascadia rupture the ability to transfer enough stress into the northern end of the San Andreas to trigger a second major earthquake there, all within a dramatically compressed window of time. If this is the first time you're hearing that Cascadia and the San Andreas might actually be connected, rather than operating as two totally separate systems, like on this video, genuinely helps more people see a story that most West Coast earthquake coverage still treats as two unrelated topics. Stop and actually sit with what a synchronized rupture like that would mean in practical terms, because this is the part that separates an interesting geology story from a genuinely alarming one. A single Cascadia megathrust earthquake on its own is already one of the most catastrophic natural disaster scenarios the United States plans for. A magnitude 8 to 9 plus event triggering violent shaking across Washington, Oregon, and Northern California, a tsunami capable of overwhelming coastal towns within minutes, and widespread infrastructure failure across a region that includes major cities, ports, and critical energy infrastructure. Now add a major San Andreas rupture happening within minutes or hours of that same event, striking California's own densely populated corridor, and you are no longer looking at one regional disaster. You are looking at simultaneous, overlapping emergency response demands stretched across nearly the entire length of the West Coast at the exact same time, right when the National Guard, FEMA resources, mutual aid agreements between states, and every hospital system up and down the coast would already be stretched to their absolute limit responding to just one of these events on its own. To put the scale of a full Cascadia rupture in perspective on its own, before even factoring in a synchronized San Andreas event, it helps to compare it to the most recent comparable disaster most people actually remember, the 2011 Tohoku earthquake off the coast of Japan, a magnitude 9. One event killed nearly 20,000 people and triggered the Fukushima nuclear disaster, and it occurred along a subduction zone with broadly similar characteristics to Cascadia. The Pacific Northwest has spent the years since Tohoku specifically studying that disaster as a working model for what a full margin Cascadia rupture could look like, because the fault mechanics are close enough that Japan's experience offers one of the most direct real-world comparisons available anywhere on the planet. Now take that baseline scenario, already one of the most severe natural disaster planning scenarios in the country, and layer a major San Andreas rupture directly on top of it within the same narrow window of time, you start to understand why researchers describe this synchronization finding as fundamentally changing what the worst case actually looks like, rather than simply adding a footnote to an already well-understood threat. This is exactly the scenario Science Daily's coverage of the study flagged when it described the finding, noting that instead of one massive quake, multiple regions could be hit at nearly the same time, and that the next big one could genuinely become a multi-city disaster unfolding all at once, rather than one contained regional catastrophe. Emergency planners who build disaster response models specifically plan around the assumption that a major earthquake will draw resources from neighboring unaffected regions to help the area that got hit. California's emergency response plans, in the event of a major Cascadia earthquake, would likely count on support flowing down from unaffected parts of the West Coast. Washington and Oregon's plans, in the event of a major San Andreas earthquake, would likely count on support flowing up from California. A synchronized rupture scenario breaks that entire assumption at its foundation, because the very regions each state's emergency plan is counting on for support could be dealing with their own simultaneous catastrophe instead of standing by ready to help. Now, it's important to be precise about what this research does and does not claim, because overstating a scientific finding does nobody any favors, and I want to be exactly as careful about this as the actual researchers involved have been. This is not a prediction that says a synchronized Cascadia San Andreas rupture is imminent, or that it will definitely happen on any particular timeline. And it is worth repeating that clearly because sensationalized versions of stories like this one tend to spread far faster online than the careful, hedged version scientists actually published. What the sediment core evidence shows is that this kind of synchronized event has happened before, in the geologic past, meaning it is a physically real possibility built into how these two fault systems interact near their shared junction, not a purely theoretical worst-case scenario dreamed up without evidence. The research is fundamentally about revealing a connection between these two systems that emergency planners, engineers, and the public had largely been treating as non-existent, and forcing a serious reassessment of what the true worst-case West Coast earthquake scenario actually looks like, rather than assuming the two faults operate in complete isolation from each other. This discovery also lands inside a much broader wave of new research that has been reshaping scientists' understanding of the entire Cascadia system over the past year, and understanding that broader context helps explain why this particular finding is landing with so much weight right now rather than being treated as an isolated curiosity. It has genuinely felt, to anyone following seismology news over the past 12 months, like Cascadia has quietly become one of the most active areas of earthquake research in the entire country, with new papers, new imaging techniques, and new discoveries about this fault system arriving at a pace that stands out even against a field that produces new findings constantly. Researchers studying the same general region around the Mendocino Triple Junction have also recently identified something else previously unknown, a hidden fragment of an ancient tectonic plate, informally named the Pioneer Fragment, a leftover piece of oceanic crust that disappeared beneath North America roughly 30 million years ago and is still down there, actively being dragged northward along with the Pacific Plate as part of this same tectonically chaotic junction. At the same time, a separate piece of the North American plate has broken off entirely and is being pulled downward along with the neighboring Gorda Plate as it continues subducting. None of this was fully understood or mapped in detail until researchers started using dense networks of extremely small, often unfelt earthquakes to build a clearer three-dimensional picture of what's actually happening beneath the surface in this junction zone. Piece by piece, the geology beneath this stretch of coastline is turning out to be dramatically more complex and more structurally interconnected than the simplified models most people grew up hearing about. So what do you actually do with a finding like this if you live anywhere along the West Coast, from Northern California up through Washington State? If you've made it this far, subscribe now, because there is genuinely more Cascadia research coming, and we're going to keep tracking each new piece as it's published. The honest answer is that the practical preparedness advice does not fundamentally change from what seismologists have already been recommending for years, but this research adds real weight to why that advice matters more than ever. If you live in a tsunami inundation zone along the Pacific Northwest coastline, know your evacuation route on foot, not just by car, because major shaking from a Cascadia rupture is expected to knock out roads, bridges, and traffic signals almost immediately, and the tsunami itself could arrive in as little as 15 to 20 minutes, depending on your exact location. If you live along the San Andreas corridor in California, the standard earthquake preparedness advice, securing heavy furniture, knowing your home's specific structural vulnerabilities, keeping a genuine multi-day emergency kit stocked with water, food, and medication, all of that becomes considerably more urgent when you factor in the real possibility that statewide emergency resources could be split across two simultaneous disaster zones rather than concentrated on a single event. And if you live anywhere near the actual junction point itself, around the northern California coastline near Cape Mendocino, you are sitting in one of the most seismically complicated pieces of ground in the entire country, where the newly discovered Pioneer Fragment, the fragmenting North American plate, and this newly documented synchronization risk between Cascadia and the San Andreas all converge in the same relatively small geographic area. That's not a coincidence of bad geographic luck. It's a direct consequence of sitting at the exact spot where two of the continent's most significant fault systems physically meet, and it's part of why this specific stretch of coastline has become such an intense focus of seismological research in recent years, with multiple independent research teams converging on the same general area using completely different methods, and arriving at strikingly complementary findings about just how structurally complex this junction actually is. There's also a broader lesson buried in how this discovery actually happened that's worth sitting with for a moment, because it says something important about the current state of earthquake science generally, and honestly, about how much of scientific progress in general comes down to persistence rather than sudden flashes of insight. This finding didn't come from a brand new satellite, a breakthrough sensor technology, or some dramatic new instrument nobody had access to before. It came from a research ship accidentally drifting off course by 55 miles, and a team of scientists who decided to collect a sample anyway, instead of writing off the detour as wasted time. That sample then sat, essentially unexplained, for over 2 decades before the right combination of researchers, the right analytical tools, and the right question came together to finally understand what it was actually showing. That tells you something genuinely humbling about how much we still don't know about the ground beneath one of the most densely populated, economically critical stretches of coastline in the entire country. If a discovery this significant was sitting quietly in a sediment core in a lab freezer for over 20 years before anyone fully understood what it meant, it raises an obvious and uncomfortable question. What else is currently sitting in a lab somewhere, already collected, already sitting in storage, that nobody has fully connected the dots on yet? Earthquake science, more than almost any other field of geology, depends on exactly this kind of slow, patient reanalysis of old data through new lenses, because the actual physical evidence, the sediment layers, the fault traces, the historical record, mostly already exists out there waiting to be properly interpreted. It's rarely a single dramatic new instrument that changes the picture. It's far more often a researcher looking at data that already existed, sometimes for decades, and finally asking the right question about it. Here's the thought I want to leave you with. For most of the history of West Coast earthquake science, Cascadia and the San Andreas have been treated as 2 separate chapters in the same regional risk story, studied by different research teams, planned for by different state emergency agencies, discussed in different news cycles whenever new research comes out about either one individually. Even the public imagination has kept them separate. Most people who've heard of the big one picture either a Pacific Northwest tsunami scenario or a Southern California ground shaking scenario, rarely both unfolding as a single connected sequence of events. This new sediment evidence is quietly starting to dismantle that separation, 1 accidental core sample and 2 decades of careful reanalysis at a time. What this discovery suggests is that those 2 chapters might actually be part of the same continuous story, connected at a junction point off the Northern California coast where one earthquake genuinely has the physical capacity to trigger the other within the span of hours, or possibly even minutes. That doesn't mean the sky is falling, and it doesn't mean this synchronized event is coming next week, next year, or even within our lifetimes. But it does mean the true worst-case scenario for the West Coast may have just gotten meaningfully worse than most emergency planning documents currently account for, and the people whose entire job is preparing this region for its next major earthquake now have to seriously factor in the possibility that when the big one finally does arrive, it might not be 1 disaster. It might be 2, arriving together exactly when the coast can least afford it, drawing on the exact same limited pool of hospitals, emergency responders, and mutual aid resources that each state has always assumed it could count on from its unaffected neighbor.